Welcome, everyone. My name is Chris Alikas. Thank you for coming to KW Video Tech virtual meetup. I hope you enjoy my spacey living room. We have okay, sorry about that. Yeah, so our first talk today will be from SSIMWAVE's Ahmed Badr. He's spent the last 3 years with SSIMWAVE, enhancing the SIM Plus video quality metric, and he's here to talk about learning and knowledge-based approaches to no reference video quality assessment. So Ahmed, if you'd like to share your screen, I think you can just do that.
Thanks, Chris. Welcome, everybody. Let me see. How do I share my screen? Yep. Okay, do you guys see the my screen now?
Yep.
Perfect. So, yeah, again, welcome everybody. And my name is Ahmed Badr, and I'll be basically talking today about no reference video quality assessment and like comparing different approaches and stuff like that. And then at the very end, I'll be basically talking a little bit more about a specific project that we worked on at SSIMWAVE, which is no reference quality assessment, basically. So this is basically the agenda. I'll start with like a quick introduction to video quality assessment. Like I'm assuming like pretty much everyone here like knows what VQA is, but I'll just touch base pretty quickly, and then we'll jump into the different approaches, and then we'll go a little bit more specific and focus on no reference, like why and what are the challenges, what are the approaches that people use out there when it comes to no reference video quality assessment, and then we'll go even more specific and focus on the learning-based versions of the no reference video quality assessment, and then we'll give one example, which is the project that we worked on at SSIMWAVE, which is the simplest, what we call the DNNR, deep neural network-based no reference. So yeah, I'll start with a quick introduction, as I mentioned, about the VQA, and as you may know, like the ultimate video quality metric, or the ultimate score, is basically the subjective score, which is basically what people would say about the quality of the video. And this goes with the mean opinion score. It's already standardized by an ITT standard, the 800.1. Like the 800.1 basically defines how to let people watch videos when it comes to like the setup, the distance from the devices, what device to watch on, the length of the sequence, even the length of the session, because people cannot watch for so long or they get tired or bored. Like the lighting setup, like there's so many like definitions in this standard, which makes it more accurate, but at the same time, it makes it very, very tedious. And on top of that, like this is a thing where humans are involved, which makes it not scalable. And it's not like a technology problem. It's just, I don't think will ever be scalable. Like there are humans involved, and it will never get super accurate and will never get super scalable because of so many reasons that you may already know. And this makes like the objective scores like sort of a necessity. It's not really an option. Like when it comes to like anything other than research, when it comes to production, when it comes to practical stuff, like people are talking about thousands of assets minimum, if not tens or hundreds of thousands. And for every single asset, there's like many, many versions of it, like different resolutions. There's like the mezzanine version, there's like the distribution version, there's different bit rates and codecs and stuff like that. And that's only talking about VOD, which is still limited compared to live broadcasts, which is 24/7, thousands of channels, which makes it literally impossible for people to collect subjective scores for all of that. So The goal for those objective scores is pretty straightforward. We just want to write an algorithm that runs on top of videos or images or frames or whatever, or sequences, uh, and convert those so many millions of pixels into a number that correlates well, or basically aligns well with what people would say when they watch the video, which is what we usually call the MOS, the mean opinion score. The goal is straightforward when it comes to definition, but it's very, very hard to achieve because so many reasons, and I'm going to just list a couple. So one of the main reasons behind this is, like, even people, when they watch the same video, they would never align. They will never get the same score. Like, and that's where the word mean in the MOS comes from. So you let multiple people, tens, watch the same exact sequence, which is like just 10 seconds long, and you will see like there is a lot of variation. And that's where you have to like remove outliers and then do the mean of the rest and stuff like that. So if your algorithm might be mimicking some, but not all the people, so that makes it a little bit more challenging. Also, like sometimes there's people that are basically a bit extreme. So same exact person watching the same video twice, he might not end up scoring it the same. And it sometimes makes sense because like it depends on your history and it also depends on your mood, sorry. So like the history affects it a lot. So for example, people watching full HD 10 years ago is very, very, like they will give that full HD video a very different score than giving it right now, like if they watch it after like all the HDR and the 4K stuff and maybe the 8K stuff. So there's memory, there's mood, and there is so many psychological things that go into this that makes it really challenging. With that said,
Ahmed,
now,
can you just hold on a second?
sure,
Can you
absolutely.
make me the host again? Sorry, just for a second. I need to just do something.
Uh, Let me see, how do I do that? Stop sharing is, now I stopped sharing. Chris, does that make you
No, you have to, I think you have to select me again and make me the host.
okay? Make host, yep.
Okay. Ahmed is the host. Okay.
Yeah, it says Abdul is now the host again.
Yep. We were just letting in some more of the participants.
Oh, I see.
I lost one of my interfaces. Here we go.
Ahmed, can you share your screen now? Do you see an option?
Yeah, I think I can. I don't need to be a host again. Yeah.
Okay, perfect.
Okay, you guys see my screen again, right?
Yep.
So yeah, with that said, I'll now talk about like how people approach this problem in general. So, so basically, there's a number of different ways when it comes to video quality assessment or even image quality assessment, and the most common or the most well-known version is basically the full reference. And in that case, you basically have, like in all cases, you have a distorted version of the video that you want to assess. And this distorted version, and sometimes you'll have access to the original pristine version. Sometimes you have access to just some information about the pristine version. And sometimes you don't have any access to it. So, and that's what makes the difference. So it's more of like a use case thing, not really an approach. So in the full reference case, you have full access to the original pristine version of the source, and you want to assess the quality of the distorted. And that's where like full temporal alignment, like if you have two streams live, then it makes it hard, but it's still possible. And that's what we do with SSIMWAVE. Like we do align the videos at a pixel level, like every single frame is aligned with the corresponding frame, and then we align them in a pixel level because sometimes there's pixel shifts, and then we start doing the video quality assessment. But this will only work if you have full access of the reference, or there's some, like we call it the reference, sometimes you call it version or the original version. And in some cases, you do have some information about the source, but it's far away, so you can't really do the whole frame, and you can't really stream all this raw data and stuff like that. So you can only get some features, and that what people would call the reduced reference. And in the reduced reference, you still need to do alignment because you want the features from the specific set of frames to align with your distorted video like scene. So at least at the scene level, you'll need to do some sort of an alignment. And then there's also cases where there is no access to any information about the source. And this will happen in so many cases. I'll talk about that later. And in that case, we call this the no reference. There's like examples in here, like the full reference is, as I mentioned, is like the most common. And we have like the PSNR, SSIMWAVE, and the SIM plus in there. We have also a reduced reference version of the SIM. And when it comes to no reference, there's like blinds and an IQE and brisk, and we also have we have a couple of no reference versions for SIM plus as well that I'll be talking about later. So now, like if full reference, like it makes sense that full reference will give you the best. Let's see. Let's just use the word accuracy in here for until we define it. So it makes sense because you have full access to the pristine source, but then like there's still a lot of investment in people trying to get a good no reference, and this is just because sometimes full reference is impossible because your source are not there. You don't have access to it. So examples, this is just a simplified diagram of the delivery chain, and you know it, like it's way more complicated than this. So this is just one version, and you'll see, like for example, the output of the camera feed right there. You see my mouse, right? Moving.
Yep.
Okay,
Yep.
so like the output of the camera feed, for example, like most of the cameras will do some sort of compression inside, so there's no such reference. There is no definition of the reference. Like the reference is the actual natural scene, which is impossible to get. So this is basically where no reference would make perfect sense. Also, like when there's a delineation point between entities, like some entities would do like the contribution encoding, and then will let other entities do the rest or some of the rest. And that's where, like, again, you like if you're like basically entity B getting the contribution encoded source, then you won't have access to the camera feed in that case, because if like because of how the uh, because of content issues or like royalty issues, I think is the word that I was looking for. So you will only have access to this version, and you want to make sure that this version is good enough before you even transcode it. So that's when no references also makes sense. Also, as you get closer and closer to the viewers, like close to homes and so on, like for example, the output of setup box or the output of the player, and that's where, again, like everything before that is like somewhere in the cloud or like upstream, and it's far from being accessible at this point, sometimes encrypted as well. And that's where, like, again, no reference would make perfect sense. So like, okay, so no reference has a lot of potential because it's very usable, and it's also sometimes not replaceable. You don't have actually any other option, but at the same time, it comes with a lot of challenges, right? So the main challenge, there's actually a number, but the main challenge when it comes to no reference video quality assessment is like you don't know what pristine is. Like there's some artifacts that are really hard to detect, like even the simple ones like blur. Like here's like two images and have like a similar level of blur, that but one of them, like the one on the top, was a bad blur. It came from like scaling a small image up to like a large resolution. But the second one was an intentional blur that came from like defocusing or changing the focus of the camera. So if you run any sort of like state-of-the-art blur detection, it will detect blur in both of them. But if you let people watch both images, then definitely the quality of the one at the bottom will be way higher compared to the one at the top. And there's so many artifacts that have the same problem. Like even like noise is one of the main interesting examples, where like I want to remind you like of the HBO intro, for example. It has a lot of noise in it, but it's intentional and people like it. But if you take like any image and add some unwanted film grain or noise or extra noise to it, people will not like it. So the same level of noise would result in completely two different quality scores from people perspective. And that what makes it a little bit easier for full reference metrics, because you have a version of the pristine, or you have access to the pristine version of the video, so you can actually always compare. Yeah, this the noise was here and was also there, then this means it was intentional, or blur and some stuff like that. But when it comes to no reference, it's really hard to tell. uh, Yeah, so now, like, how did people approach this no reference video quality assessment? So there's so many ways, but I just wanted to sort of like, instead of listing all the different approaches, I wanted to like go a little bit like a couple steps higher and just focus on. I'll try to basically convert this whole problem into a two-stage problem. So in most of the cases, at least as far as I know, all the algorithms that I know of, they have like at least a notion of these two stages. One of them is like the feature extraction, and the other stage that comes afterwards is basically the modeling or the mapping to quality. So if you think about these two stages, you have like frames coming in, and then you extract features, and those features can be anything pretty much. So, but I have them here split into like two main uh, kinds of features. Like some of them are like bit stream level, so like even before decoding, by just looking at the bit stream, so you can know a little bit more, like you can know more about the video like by just looking at the codec, the bit rate, the packet loss, frame rate, stuff like that. Or you can do like a bit more investigation, decode the video if possible, and do like more statistics on the content itself and the artifacts. So can be like detect blur, the level of blur, the level of blockiness, how much noise are there, and then you can also do like more about the content itself, not just the artifacts. So you can just measure how much information is in the content, how much texture, how much motion and stuff like that. And then there's so many features that come out of this stage that go into the next stage, which takes all those features and then build a model that can be a mathematical, knowledge-based, or a learning-based. And even the first stage, I forgot to mention that even the first stage, the feature extraction stage, can still be knowledge-based or learning-based. So it can be like, yeah, Fourier transform or a DCT transform and then do analysis in the frequency domain, or it can be just feed frames in and try to and into a neural network and then detect what the blur is or what the noise is and stuff like that. So it can be any of that, and the same happens in the modeling stage. So you take all those features that have been created through like a knowledge-based or learning-based approach in the first stage, and then again you do the same thing again. You use a machine learning-based approach, or a knowledge-based mathematical model that converts all those so many numbers into a one quality number, basically. And that's where like it's hard to tell if the full approach is learning based or is knowledge based. So we would only call it knowledge based if both stages are knowledge based, and we would call it learning based, I think, if any of them is learning based. And that's where like it's a bit confusing. It's hard to label algorithms when it comes to no reference video quality assessment. And then while doing the mapping, you also want to do like mapping is all about like optimization. You're trying to basically map your features into a quality while aligning with MOS scores. And aligning here means so many things in math. It can be like minimizing the error. It can be maximizing the correlation, and we'll talk about that later as well. So I think I want to make this as interactive as possible. I forgot to mention that earlier. So like, if you guys have any questions, I think feel free to stop me and ask questions.
Or you could post questions in the chat, and we can can do that at the end. But
sure.
Wherever you feel needed.
That will work too. Yeah, thanks, Chris. So, like as I mentioned earlier, like the research team and at SSIMWAVE has investigated this problem from day one, and like I've been with the company for like more than 3 years now, and we've been basically focusing on video quality assessment as this is like basically the bread and butter of SSIMWAVE, and specifically on the no reference video quality assessment. And in the last year or so, maybe slightly more than a year, We have been so much into that problem. We have made a lot of improvements by switching to learning-based video quality assessment. So we have a lot of experience that I wanted to share some, but not many, because there's a lot of IP around this. So I'll try to balance between these two. So uh, so I'll start with how do I think designing a learning-based no reference, how to go about this problem, designing a learning-based no reference video quality assessment. So it's I think there's a couple of things that we one has to be uh, very considerate about when it comes to designing a no reference video quality assessment. And I'm going to list four in here. I hope I did not forget anything. But the first one I think is the video data set. We have while creating the final version or the first production version of our simplest no reference video quality assessment algorithm, we went through so many different versions in the middle that we were not super happy with. And one of the problems that I remember was basically if you if you missed one of the content types, and a content type here does not mean actually uh, the generic content type, it's not the movie versus sport. No, I actually mean a very, very specific type of content down to a specific sport with a specific background. So if you did not feed the network any of that, it might be learning something completely different than what you wanted it to learn. So the behavior will be very unexpected if you exclude one of those content types. And I remember one of the cases where we fed the network a lot of uh, uh, what do we call this, slates, videos that are basically frozen. There's no motion, and most of those videos were on the high quality, because whenever you compress static videos, the quality is always high because it's easy. And most of the videos that we had in the network were very high quality. I mean, the videos with the static videos with high quality. So even if you after this is in the training phase, and then in the in the feed forward phase, we realized that whenever you feed a static video to the network, it will say that the quality is high, even if the quality was low. So this is what the network ended up learning, and that's not what it was supposed to learn, and that's where you have to be very, very careful when you select your video data set. The next thing that I think is also as important is your ground truth. So again, if you want to train a network to do something that complex, which is basically mimicking a human visual system or a human brain when it comes to watching videos, which is very, very complex, you have to be very careful when you select your ground truth. So, um, so, so basically, and at the same time, your your ultimate ground truth, as we may all know, is basically the MOS score, the mean opinion score. But then with the first point in mind, you want your video data set to be huge, to cover all the different aspects, all the different types, all the different codecs, not all of them, the ones that you care about for this use case, all the codecs, all the artifacts that you care about, all the content types that you care about, frame rates, and so on. It makes it huge, not thousands, not tens of thousands. We're talking about millions of samples, and it's just impossible to get people to watch millions of samples and score them. So MOS is just out of scope. It's not possible. So you have to select an objective video quality metric and use this as a ground truth. And we clearly selected Simplus, not just because it's ours, there's also other options out there that are basically free, but we also know that Simplus is the only full reference that basically takes human visual system in consideration when it was first designed. And that's exactly what we wanted to do. And it also correlates the highest among all the other metrics when it comes to public subject rated video databases. And that's basically the main two reasons behind selecting it. And that's basically how we ended up doing it. Now, the third question that you'll come across is when you build your network, you're basically trying to optimize something. You're trying to basically, as I mentioned earlier, try to minimize or you're trying to basically align with how people watch videos, which is basically the MOS score. The word align here is not mathematical, so align can mean so many things. It can be maximizing a correlation coefficient. One kind of a correlation coefficient, like might be the PLCC or the SRCC or the KRCC or whatever, or it can be minimizing some sort of an error, like it might be the mean square error or the mean absolute error. So again, this is also a hard question. It's very, very technical, and you have to be very careful while selecting which one. It and what we figured is it's more of a use case specific. So I'm not sure be able to elaborate a lot about this, but in a nutshell, it basically it comes down to if you're focusing on a very, very specific use case, like a specific codec, a specific quality range, then maybe you want to reduce your error. But if you're focusing on something that is a generic, general purpose that works for like so many codecs, so many artifacts, so many frame rates, and so on, like a very wide quality range from 1 to 5 on an MI scale or whatever, then maybe a correlation coefficient is the right thing to do. The fourth and the last question that you want to ask yourself while designing learning-based NR VQA is what model and what architecture are you going to use? So the model question might be a little bit easier than the architecture because like it is already like neural networks, especially convolutional neural networks, are like well established to be designed are actually meant to be designed for image processing in general. So it makes it easier to just select convolution networks in here. Uh, and then basically when it comes to the architecture, uh, then that's basically a hard problem again. It's even harder than the third question. And again, we'll not be able to elaborate a lot more about this. There is already a lot out there, like different versions, people trying at an individual level or at companies or in research papers trying to like come up with a no reference video quality assessment using neural networks. Uh, and it's usually a convolution neural network, but then they're different when it comes to do they use fusion or not? Do they use a lot of fully connected layers? Do they use like a deep network or just a couple of layers and stuff like that? And again, I won't be able to mention exactly what we ended up using in our simplest, but yeah. So I covered most of this in the previous slide. So this is basically trying to answer the question on how to prepare the video data set. So again, you have to think about so many aspects. You have to think about the type, and the types are not just movies and sports, but you have to go specific into types of sports and types of movies, the types of scenes like slates and logos, and like you have to be very, very thorough, or you won't be able to expect what the neural network is gonna, or what the model is gonna behave on such contents. Again, you have to think about spatial, temporal. You have to also think about frame rates and stuff like that. So when it comes to artifacts, again, it's not about being thorough anymore. It's about being like, because if you want to cover the whole world, you're going to end up with either like a network that doesn't work or a network that's humongous. Like it's not practical. So you have to be very careful when you select what is it that you have to answer this question specifically. What is it that you want to cover? Do you want to do like compression artifacts only? Do you want to do filtering artifacts like noise denoising and stuff like that? Or do you want to do like scaling artifacts or network impairments? So you'll have to be, you can still do a combination. I'm not saying you can't. I'm just saying like the more you add to it, the more complex it gets. And like you'll have to balance between it's a very, very complex network versus it's an accurate one versus the third dimension, which is how much do I want to cover. So you'll have to balance between all these three dimensions basically. Again, the ground truth, I think I talked about that already. And one thing that I did not mention when it comes to like selecting your objective score is you want a subjective score, again, that is that aligns with how people watch videos. And at the same time, it covers your use case. So if you really want to build a no reference video quality assessment for HDR videos, so you can't really use PSNR or VMAF or any of those. You have to use one that basically supports HDR, like Simplus, for example, in that case. And that's actually another reason on why we ended up selecting Simplus, because we wanted to extend our no reference video quality assessment to cover HDR as well. And there's like the cross resolution part of it. Some metrics, some full reference metrics would cover that, some wouldn't. So I have to be careful with that as well. Um, yeah, also touched on this earlier, and this is basically how do you select your loss function in AI model, and I think I covered all that, especially the loss function part. Again, if you really are focusing on one specific use case, like maybe JPEG 2000 compression at high bit rate, which is going to always be like in the high quality range, then maybe you want to do a more MSE and MAE, like minimize error. But if you really want to do a more general purpose one, then again, correlation coefficient might be the right thing to do. This is just a rule of thumb. It's not really a theory or a theorem or whatever. And again, for the AI model, then then anything that has any sort of an AI in it is called an AI. So it's only called a knowledge based if everything in it is knowledge based. So there's sort of three options. You can have like a knowledge based feature extraction and then a regression model to convert those features into a quality, or you can have a learning based feature extraction. That's like a neural network, like a lightweight neural network, and then another separate regression model, or you can do the whole thing one shot. That's all AI or machine learning based. And that's what we actually selected in our Simplus DNNR approach. So I'm basically in this slide answering all the 4 questions that I posed earlier. Like I'm just basically presenting how we, SimWave, answered those questions. So for the databases, we ended up with like tens of millions, literally tens of millions, not just a number on a slide here. And when it comes to like different scenes, like those millions of samples come from like different frames of the same scene, but also different versions of the frame, like encoded differently, filtered differently, different quality levels and stuff like that. But when it comes to scenes, we ended up with thousands of scenes from more than 30 different content types, and the range of quality is literally full. Like we have like we use a scale from 0 to 100, and we have like qualities from like the 5 and 10 all the way to the 100. So we wanted something that is general purpose, because as I mentioned earlier, we deploy, like SimWave products deploy at scale at pretty much throughout the whole delivery chain. So our use case is kind of more general. It's not just specific for sources or specific for distribution. Um, not specific for OTT versus uh, uh, a cable or stuff like that. So like we sort of deploy in all of these. So we wanted a network or a model that works in all those cases. So we wanted something that is more general purpose. And that's why we wanted to cover all of it, pretty much all, because you will never ever cover all the content types, I guess. Um, but we tried to cover all the content types, all the quality range that we can think of, the codecs that we care about, and stuff like that. And when it comes to ground truth, again, the answer was simple, because we know Simplus aligns with the human visual system and aligns with MOS scores, like that correlates the highest among the rest. And it also supports the cases that we wanted to support, which is the HDR use case, the devices. Like for example, the same video, if you watch it on your phone, will be different than watching it on a 65-inch TV. So Simplus also takes care of that, and we wanted our neural network VQA approach to also take care of that. This basically made it easy for us to select or to answer that second question. When it comes to the network architecture, like there's a lot of research and that we built upon that made this question, half of it, easy to answer when it comes to what model to use. But again, we had to go and revisit a lot of the architecture to make it more practical. So none of the architectures that were already in the in papers or in research papers and articles were never like very practical. When you do research, you don't really focus a lot about practicality, like how, like you want something to be real time, for example. That's not a research thing. Research is more into into like correlations and accuracy and stuff like that, which is important. And that's where we basically came in. So we built upon a lot of like years, like at least 3 or 4, maybe 5 years of work, research work that was done with a collaboration with universities and stuff like that. And then we the team, like the research team in SSIMWAVE, like built upon this, and basically they pretty much modified the structure, most of it, but kept the main principles and to make it more practical and to cover more use cases. Like for example, the HDR was not there, like it was not covering all the codecs that we wanted, so we added all that and so on. So we added a lot of more features. At the same time, we reduced the complexity. So we came up with that balance. And this is basically the result. This is what we ended up with. So in this case, those are basically every single point on this plot is I think a video sequence that is very, very short. I think 5 seconds, maybe 10 seconds long, or maybe a mixture. And then on the x-axis, it's the simplest full reference. So this is our grand truth in this case. And we know simplest full reference correlates like more than 90% with MOS scores or human scores. And then on the y-axis is the no reference, the simplest DNR, which is the no reference version, the latest no reference version of simplest. And just to remind everyone here, the simplest node reference only looks at the distorted. The simplest full reference has access to the full, has access to the original pristine source. So the simplest full reference takes 2 frames and it gives a score. The simplest no reference, the DNR on the y-axis, takes just the distorted, the 1 frame, and it gives a score. And this is basically how much they align. The Pearson Pearson correlation coefficient is like a 93.9375. So we call it 93% here, or 94%, and this is way beyond any other no reference that I know of. Like I don't want to list names and numbers, but like the state of the art is basically between the 40 and 60%. So it's a huge improvement, and at the same time it's real time. Like we already right now, as I speak, we have that deployed in on thousands of channels running in real time, not just assets, VOD assets, but actually linear broadcast channels. And those videos, the ones that we plotted in this plot or in this figure, are not the ones that we used for training. These are just exclusive set of videos that were only used for validation. Like when it comes to training, it's the numbers are way higher, but they're not as relevant. And that's what we thought, like we should be sharing this. Again, this because we used simplest as a full reference as a ground truth. Like we had so many features that basically came handy. Like for example, the device support, the wide range of resolutions, and the HDR, the dynamic range, and the frame rates, and codec agnostic part of it. So you see, like here, like we're just plotting like 3 codecs, and the correlation is basically pretty much as high for all 3 codecs. Yeah. So I think this pretty much concludes basically my presentation. I just want to end the presentation with just the one thing that I want everyone to remember, if you guys will remember anything of this talk, is that if you're about to start, or you already started doing like building an AI-based approach, I think these are like the 3 things that you have to be careful while doing. You have to basically build a framework that is uniform when it comes to content understanding. And by that, I actually mean that try to not separate the feature extraction part from the modeling part. Like do not, like this did not prove to work well. At least let's just not say that it proves that it doesn't work, because all the approaches or all the algorithms that use that approach, where there's like a feature extraction that is completely separate from modeling, it didn't turn out to be like very accurate. So something uniform that does everything one shot, because this is basically how our brains work. And you're trying to build a neural network with millions of neurons, or at least hundreds of thousands of neurons that mimic how our neurons work. And this is basically how our brain works. It watches the video and it gives a score. It doesn't try to like extract features and look, oh yeah, there is blur in here, and there's compression artifacts in there, and there's macro blocking in there, and that's why my score is going to be 20. This is not how our brains work. The second thing is like extensive coverage. Maybe I did not use the best word in here. I think I meant cover the content and artifacts that you care about. If you're, for example, if you're Netflix, you don't do sports, then maybe you shouldn't be caring much about sports when you build your network. But if you're a company that does sports and does natural scenes, then this is the content you should be caring about. If you're an OTT company that does not care much about macro blocking because you do TCP and stuff like that, then do not add macro blocking to your network, because this will only either increase its complexity or will reduce its accuracy. So be careful while selecting your content and artifacts that you want to cover, and aspects in general. And again, ground truth is very, very important. If you build if you build a network that uses PSNR, you're going to only be as good as PSNR. PSNR correlates around 70% with MOS scores. So even if you build a network that correlates 99% with PSNR, your overall will only be 70%. You'll only be as good as your ground truth, basically. So you have to also be careful with selecting your ground truth. Yeah, I think this is what I wanted to leave you with, and this will conclude my presentation.
Right.
Thank you.
Thanks, Ahmed. So open the floor now for questions. Feel free to just unmute your mic if you have any questions for Ahmed. Okay, just checking the chat. Yeah. So thanks, Ahmed. Robert, I think
Thank you.
you're up. So